Hello, this is Dr. Haribhaskar from Department of Mathematics, Christ, Bengaluru, India. Many problems can be solved by attempting to model it in terms of mathematical notations. Depending on the models, different solution techniques can be used to solve and arrive at the solutions to problems. Our focus of study will be on types of models that have mathematical objects such as objective function and constraints, in which by depending on these constraints, the objective function can be either maximized or minimized. By objective function, we mean that the entire problem of study has an objective to be achieved, and that objective is modeled mathematically into an objective function. By constraints, we mean that the entire problem of study can achieve its objective subject to certain restrictions only, and these restrictions are modeled mathematically and are termed as constraints. Moreover, every object we encounter in our study will be linear in nature. In simple terms, by linear we mean that every term of the mathematical expression will have only one variable with power 1. The mathematical models of this type are referred to as linear programming problems. For example, a two decision variables dependent linear programming problem may appear as. In this example, the mathematical object z is equal to 3x plus 2y is called an objective function which is to be maximized, and hence we write it as maximize z is equal to 3x plus 2y. Mathematical objects 2x plus 4y less than or equal to 7, 3x plus 7y less than or equal to 9, x comma y greater than or equal to 0 are called constraints. In particular, the constraints that are in the form of x comma y greater than or equal to 0 are referred to as non-negative constraints. From a well documented literature on the original problem, we can formulate a linear programming problem. Let us first choose such a literature and try to formulate a linear programming problem. ReadyMix produces both interior and exterior paints from two raw materials M1 and M2. The table provides the basic data of the problem. The maximum daily availability of raw material 1 is 24 tons and that of the raw material 2 is 6 tons. To produce 1 ton of the exterior paint, 6 tons of raw material M1 and 1 ton of raw material M2 are required. To produce 1 ton of the interior paint, 4 tons of raw material M1 and 2 tons of raw material M2 are required. A market survey indicates that the daily demand for the interior paint cannot exceed that of exterior paint by more than 1 ton. Also, the maximum daily demand for the interior paint is 2 tons. Profit per ton of the exterior paint is given as 5 and that of the interior paint is 4. ReadyMix wants to determine the optimum product mix of interior and exterior paints, and that maximizes the total daily profit. So, we have to formulate this as a linear programming problem. Since ReadyMix wants to find the optimum product mix of the interior and exterior paints, we need two decision variables. Let x and y be those two decision variables such that x is equal to tons of exterior paints produced daily and y is equal to tons of interior paints produced daily. Given that the profit per ton of the exterior paint is 5, hence the profit on x tons of exterior paints produced is 5 times x. Also, given that the profit per ton of the interior paint is 4, hence the profit on y tons of interior paint produced is 4y. So the total profit on producing x tons of the exterior paint and y tons of the interior paint is P is equal to 5x plus 4y. So, to optimize the profit means is to maximize the total profit P. Hence, the objective function P is equal to 5x plus 4y is to be maximized here, and we denote it as maximize P is equal to 5x plus 4y. Also, it is given that 6 units of raw material M1 are required to produce 1 ton of exterior paint. Hence, to produce x units of exterior paint, 6x unit of raw material M1 are required. So, likewise, since it is given that 4 units of raw material M1 are required to produce 1 ton of interior paint, 4 y units of raw material M1 are required to produce y units of interior paint. Hence, the total raw material M1 required will be 6x plus 4y. But the maximum availability of the raw material M1 is 24 tons. Hence, the raw material M1 used for producing the paints cannot exceed 24 tons. So, therefore, we have the constraint 6x plus 4y less than or equal to 24. By means of similar argument for the data provided on the raw material M2, we have the constraint x plus 2y less than or equal to 6. The excess of the interior paint produced than that of the exterior paint is y minus x. But it is given that this cannot exceed 1, so we have the constraint y minus x less than or equal to 1 or minus x plus y less than or equal to 1. Since the maximum daily demand for the interior paint is 2 tons, y cannot exceed 2, hence we have the constraint y less than or equal to 2. Moreover, since x and y are quantities, they cannot be negative, that is, we have x comma y greater than or equal to 0. This is how we formulate a linear programming problem. As this linear programming problem is a 2 variable problem, it can be solved by a graphical method. To solve this by this method, we have to represent all constraints graphically. Since x and y are greater than or equal to 0, represents a non-negative constraints, we shall restrict the graphical representation of the remaining constraints only in the first quadrant. Consider the constraints C1 given by 6x plus 4y less than or equal to 24. Since this constraint represents both the inequality and the equation, it can be represented as a region graphically such that the region includes the points satisfied by the 6x plus 4y less than 24 and 6x plus 4y is equal to 24. To achieve this, first represent 6x plus 4y is equal to 24 graphically. We need 2 guiding points to draw this straight line. This can be easily done by setting y is equal to 0 to find x and x is equal to 0 to find y. Hence, we have 4, 0 and 0, 6 as guiding points to represent the straight line 6x plus 4y is equal to 24. By plotting these 2 points and joining them, we get the graphical representation of 6x plus 4y is equal to 24. This line cuts the quadrant into 2 regions. One region is towards the origin and the other away from the origin. Any one of these 2 regions only will satisfy 6x plus 4y less than 24. Note that none of these 2 regions include the graph of 6x plus 4y is equal to 24. By substituting a point that does not belong to 6x plus 4y is equal to 24 and belongs to any one of these 2 regions and verifying its satisfiability, it is possible to identify the region. Let us choose the point with the coordinates 0, 0 and hence substitute x is equal to 0 and y is equal to 0 in 6x plus 4y less than 24. Then we get 0 less than 24, which is true. This indicates that 6x plus 4y less than 24 is represented by the region marked towards the chosen point, which is the origin, that is, the region marked towards the origin satisfies 6x plus 4y less than 24. In case if this point does not satisfy 6x plus 4y less than 24, then we have to choose the other region. So, therefore, the region of 6x plus 4y less than 24 along with the graphical representation of 6x plus 4y is equal to 24 gives the graphical representation of 6x plus 4y less than or equal to 24. In this graphical representation shown, the blue lines represent 6x plus 4y is equal to 24 and the arrows that point towards the origin represent the region for 6x plus 4y less than 24. Let us hereafter represent the constraints like this. Now, considering the constraint C2 given by x plus 2y less than or equal to 6 and computing in the same manner as we did for 6x plus 4y less than or equal to 24, the region of the constraint C2 given by x plus 2y less than or equal to 6 is represented graphically, which is shown along with the graphical representation of the constraint C1 given by 6x plus 4y less than or equal to 24. Likewise, also by adding the other two constraints in the same graph, we have the graphical representations of all the 4 constraints restricted to the first quadrant only. Now notice that all the 4 regions overlap in the first quadrant, and that region is shown as A, B, C, D, E, F, A. This region, which satisfies all the constraints including the non-negativity constraints, is called as the feasible region. The points A, B, C, D, E, F are called the corner points of this feasible region. By theoretical inputs on the study of this feasible region, it has been proved that one of these corner points will provide the optimum solution for the problem. Hence, it is sufficient to find the coordinates of these points and the value of the objective function only for these points. Since A is the origin, A is given by the x coordinate 0 and y coordinate 0, which we shall denote as 0, 0. B lies on the x axis at a distance of 4 from the origin, hence B is equal to 4, 0. F lies on the y axis at the distance of 1 from the origin, and hence F is equal to 0, 1. C is the intersection of the straight line given by 6x plus 4y is equal to 24 and x plus 2y is equal to 6. Hence, by solving these two equations, C is equal to 3, 1.5. D is the intersection of y is equal to 2 and x plus 2y is equal to 6. Hence, D is equal to 2, 2. E is the intersection of y is equal to 2 and minus x plus y is equal to 1. Hence, E is equal to 1, 2. Thus, we have the coordinates A is equal to 0, 0, B is equal to 4, 0, C is equal to 3, 1.5, D is equal to 2, 2, E is equal to 1, 2, and F is equal to 0, 1. The value of the objective function 3x plus 2y at these points are the maximum among 0, 20, 21, 18, 13 and 4 is 21, which is obtained at the point C. Hence, the solution for the given problem is x is equal to 3, y is equal to 1.5 and the maximum value is 21. That is, when tons of exterior paints produced daily is 3000 units and the tons of interior paints produced daily is 1500 units, the maximum profit is 21,000. So, in this video we have learned to formulate a linear programming problem from the given literature and also learn to solve the same by representing the constraints graphically. Solving graphically is possible only if the two decision variables are available in the linear programming problem. In case there are more than 2 variables, then we have to solve by a more general method called as a simplex method, which we shall see in the next video. Thank you.